Hello students of statics, this is Dr. Dan Baker with a video today getting into a new chapter, and this chapter is talking about equilibrium of particles. We're going to have several chapters that will focus on equilibrium here in statics, and this is the first, the simplest one, and that is specifically talking about particles. And so let's start off with some definitions so we can kind of get on the same playing field of what we're talking about. So what is a particle? A particle, we could say, is an object with a mass, but a tiny size. Using calculus type words, we could say it's infinitesimally small. Okay, that would be the definition of a particle. And that definition is going to hold for both statics and also dynamics. Okay, so we'll stick with that one. And then equilibrium, thinking about what is this equilibrium? Equilibrium is really saying that we have a balance of forces. So a balance of forces really comes back to Newton's second law. Sum of forces as a vector equals ma. Now we talked about a little bit, talking about Newton's laws, that our acceleration in statics is always going to go to zero. Dynamics it won't, but statics will always go to zero. So what we're left with in this equation is really just that the sum of all forces in all directions equal zero. And that's the fundamental equation for equilibrium of forces. Now, noting that this takes perfect care of basically saying that there's going to be no translation. The force equation actually has nothing to do with rotation, but it turns out that the reason that we can use this equation alone for particles is that all particles have what are called concurrent forces. And concurrent forces intersect at one point. Okay, so if we have a particle, and say this particle has a weight, it has a mass and it's here on Earth, it could have a weight. And let's say that there is one rope pulling up in this direction, pulling with some tension, another rope pulling up in this direction. Call this one T1, call this T2. And so really what I've just done, and we'll talk about this more as we move forward, I've created a free body diagram of this particle and represented the loading on that particle, which is that loading of the weight, and also it's what are called reaction forces. I'll get more into those as we move forward. But the key thing here I wanted to highlight is that the lines of action of all of these forces, okay, tracing out these lines of action with dotted lines, all intersect concurrently at that particle. Okay, so this idea of intersecting at one point. And so really you could think it's that the lines of action intersect at one single point. We know that we can move those forces anywhere along their line of action, right? Remember that if I grab a hold of let's grab the weight force. I could draw the weight force up here. I could draw it even further up here. And it's exactly the same weight force even as if I drew it all the way down there. Okay, so I'm just sliding it along its line of action, and the lines of action of all three of these forces intersect at one place. Now it turns out that we can use this particle approach also on rigid bodies. And the reason that we can do that on rigid bodies is directly related to this idea of concurrent forces. And so let's say that we have, this is a rigid body, and hypothetically, let's say that there's something pulling here on this end with a tension. Let's say the weight force is acting here. And let's say that there is a third force, maybe another cable or something attached up here. Okay, so let's use that same tension 1, tension 2, and weight. And again, if I extend out these lines of action, and my drawing was fairly accurate, what I see is that all these forces are concurrent at that one single point. Okay, so there actually are quite a few rigid bodies we can treat as particles. if all their forces are concurrent. Okay, so getting into solve this equation, sum of forces equals 0. There's a little bit of difference between two-dimensional problems and three-dimensional problems. So on two-dimensional problems, you'll use your sine and cosine, your right triangle trigonometry relationships, to find directions, right? So if you break things into components and you want to find, say, T2 up here, and we knew that its angle from horizontal was theta, and we established an axis system, let's say x is going over the right and y is going up, we would know that the x component of T2, go ahead and write these out, so we'll say T2 as a vector in the x is going to be negative T2 magnitude cosine of theta, that's the adjacent side, and then the vertical component will be positive, so that's going to be T2 sine of theta. Okay, so just basically saying use your sine and cosine, just like you did in physics, to find the directions of these vectors. In three-dimensional problems, we learned a tool in chapter 2, which is unit vectors. So in 3D, we want to use unit vectors for directions. Now, while you could also use coordinate direction angles, Now, while you could also use direction cosine angles, the reality is when you're working through a direction cosine angle, you're fundamentally dealing with unit vectors anyway. Okay, so if you're calling it a unit vector component or calling it the cosine of a direction cosine angle, those things are one and the same. And so for two dimensions, we have two fundamental equations. Sum of forces in the x equals 0, and sum of forces in the y equals 0. So two equations can satisfy two unknowns. In three dimensions, probably no surprise, we're going to add one more force equation. So sum of the force in the x equals 0, sum of the force in the y equals 0, and sum of the forces in the z equals 0. Okay, so we have two equations up to two unknowns here for two dimension, and then we have three equations allowing for up to three unknowns for our three-dimensional problems. All right, that lays out some of the basics. There's a few more details that we want to get into, and one of those is to talk about two force bodies. Now, the definition of a two-force body is actually right in the word. It's actually a body with two forces. But it's really in learning to recognize what are two-force bodies is one of the really critical things to learn early on in statics. Okay, and so if you put some effort into anything on this section, if you're like, oh, I understand all this equilibrium stuff, put some effort into understanding what are these two-force bodies. And so, try kind of a full definition. Two-force bodies have only two applied / body forces. So essentially two forces total. So if you have a weight and a cable force, that'd be your two forces. You can't have any others. And for these two force bodies to be in equilibrium, these two forces have to be balanced, right? So to be in equilibrium, the forces must be equal opposite, so opposites pointing in opposite directions. And 3, they need to share the same line of action. Let's write this as LOA, line of action. Okay, so if they're equal, they're opposite, and they share the same line of action, then they can actually be balanced. They can also then be basically applied to a body and put in equilibrium. So if we have a situation, like I said, if we have a block which has a weight force, and let's say this block is sitting on, I'll draw this in gray, just kind of ghost it out there, sitting on a horizontal surface. If I remove that surface, I can remove that surface and replace it with a normal force. Because we don't leave the, we'll talk a bit about that going forward, but we want to isolate this body, okay? And so this block would be a two-force member. There's two forces. These forces are equal, they're opposite, and they're sharing the same line of action, which in this case would be a vertical line of action. It turns out that there are two different ways that a two-force member can be loaded. One of those ways is in tension. And tension will always pull. And the other way that a two-force member can be loaded is in compression. And compression always pushes. Okay, and that's fundamentally the only two ways that a two-force body can be loaded. Okay, the forces either can be pointing at each other. So if I drew a little, here's a member, and here's a member, a little rigid body, so tension is always going to pull. So this would be a two-force member, and compression would always push. Okay, push on either end of that member, squeezing it together. All right, so another piece of information, and this is kind of general for statics, is dealing with frictionless pulleys. And so frictionless pulleys, what we're saying here is that a frictionless pulley has no friction at the pin. Okay, so essentially it would spin freely. So frictionless pulleys have no friction at the pin. A massless pulley, I won't write out a definition for a massless pulley because once again, it's in the statement. A massless pulley has no mass. And when you have these two things together, a frictionless pulley plus a massless pulley, you end up with a convenient situation that cable tensions are equal. That is in magnitude. So let's look at a quick little diagram that would show this as an example. Let's say that we have a ceiling up here, so this is non-moving. A floor down here, also non-moving. And I have a pulley. This is a frictionless massless pulley. Another frictionless massless pulley. And then a third frictionless massless pulley coming off the floor, that if we hang say a 20-pound, this is pounds force, block from a cable, this cable would come up around this pulley, down around the bottom one, back up and over here. What it's really saying is it's just going to pass that 20 pounds through that entire cable. So the entire cable will have a tension of 20 pounds, including all the way over there to the left. Now, once again, that isn't always true if you had pulleys that included friction and also pulleys that include mass. But for statics, In the entire class, except for one section in the friction chapter dealing with journal bearings, we can assume that we're always dealing with frictionless, massless pulleys. All right, so the last thing I want to cover here is talking about free body diagrams. Now, I hope that you are a free body diagram expert. Because if you are, it'll make your life in statics just so much easier. The reality that I see of students coming in from physics into statics is that many students have a number of fundamental errors in their conceptual understanding of free body diagrams. Okay, so we're going to be pretty methodical about them. You'll get a lot of practice in creating them. Hopefully we'll find those errors and we can keep moving on. But basically the free body diagram is the source of all of your forces for your sum of forces equals 0. So you can really think that the free body diagram is like a graphical representation, and the sum of forces equals 0 is an algebraic representation. I'll just put it as a math representation. Okay, so you create the free body diagram first, always first, and then create your equations from there. And so to create a free body diagram, we have multiple steps. The first step is to isolate your body. And really what that's saying is to choose what body, what rigid body, or what assembly of rigid bodies that you want to create a free body diagram for. Okay? And so when you isolate, you fundamentally cut away everything else that's around that item. Okay, so in this case here, if I isolated this bottom pulley, I would cut around where that yellow line is, and I can see I cut two different tensions around that pulley. And we'll come back to that example here in a second. The second thing we need for a free body diagram is an axis system. If we are going to sum forces, we're going to tend to use some force X, some force Y. We need an axis system in order to determine what is the X direction, what is the Y direction. Our third step is to load the free body diagram. So just to show you these first three steps, let's say that we have one of the simplest 1D problems that we could create, which would be a block which is hanging from a cable. Okay, and let's say this is 10 newtons. Okay, so this would be my problem sketch. This is not a free body diagram. Okay, this is a problem sketch. So to isolate the body, I take a look and I say, well, if this problem asks me to solve for the tension in that cable, I would isolate around that block. So after I isolate the body, I'm going to redraw it. So here is my block. I'm going to add an axis system. Now I'm going to make a two-dimensional axis system on here, even though everything will actually be happening in one dimension on this problem. I'm going to use a standard horizontal X, vertical Y. I'm then going to load that block. My load is the body force, the weight of 10 newtons. Okay, that is the only load that's on that body. After we load it, we are going to add the reactions. And the reactions are the forces which essentially balance the applied loads to keep things static. So in this case, a reaction is going to be this tension. And so there we have a perfectly formed free body diagram. Now the only thing that we'll add in, and this will mainly be into chapter 5, and it's also step 5, is we're going to add dimensions. Now if you remember the term torque from physics, torque and moments are basically the same thing. We'll get into those in chapter 4, which is the next chapter. But when you need to take and find the torque of a force, the moment of a force, you need distances to that force. Hence, we need dimensions on our free body diagram. But here in chapter 3, you really don't need dimensions because all we're doing is summing forces, and the forces are independent of any kind of dimensions. Okay, and so after you have your free body diagram, then you can create your equilibrium equations, and then you can solve your problem. Okay, so a free body diagram creates equilibrium equations, then you basically get into your math to solving that problem. And that is the fundamental process. It doesn't matter if it's a two-dimensional problem or a three-dimensional problem. Obviously, the math is a little bit heavier in a three-dimensional problem because you can deal with up to 3 unknowns, but it's still the same fundamental process. Create a free body diagram, write your equations equilibrium, and then solve for your unknowns, which remain in those equations of equilibrium. I hope that this laid out equilibrium for you very clearly. Please feel free to follow up if you have any questions, and I appreciate your efforts.